The primary objective for this experiment was to create a turbine and using the downstream flow of water generate electricity by converting the mechanical energy of the water hitting the turbines into an electrical energy through the motor that was connected to the turbines. A hydroelectric turbine is a device that converts the mechanical energy of flow of water into electrical energy through a generator. This can be done using the following parameters: the flow rate of water, the kinematic viscosity, the density of water, Reynolds number, and the pressure head. So first we calculate the power output using the kinematic viscosity and the flow rate of water. This power output can then be checked through the equation of efficiency by using the output power and input power. To scale this experiment on a larger scale, we can use the concepts of computational fluid dynamics and the Reynolds number to a desired Reynolds number of the natural flow of water and optimize the blade designs to predict the performance of the turbine to getting optimal flow of water and generate optimal amount of electricity.
A 2-gallon bucket was modified with a slot cut to allow water from the stream to enter the center and interact with the turbine. The slot was cut with a guide created to divert the flow of water, allowing the turbine to spin clockwise and prevent water from causing the blades to face any resistance from water flowing in the opposite direction within the bucket. The turbine was connected directly to the motor, which was connected to the breadboard with the four diodes to create the rectifier and allow the AC voltage or Y voltage to be turned into DC voltage for measuring. When the flume is activated and water begins to flow through the turbine and the voltage and current outputs were measured via multimeters connected to the circuit, the flume's water velocity was changed by changing the angle of its slope and height which it came out from. This provided two data sets when the heights were at 1 inch and 5 inches.
The results from the experiment were determined so that power could be generated with a small-scale hydropower turbine. Two sets of data were collected, which gave a relatively consistent output of power for each flow rate once the turbine was spinning to a certain speed. These data sets were taken at different heights and angles of slope, which produced velocities of 0.39 meters per second when the height of the flume was at 1 inch and 0.423 meters per second when the height of the flume was at 5 inches. Below is a Excel sheet tab which has all the information for current, voltage, velocity, as well as power, the theoretical power that we should have got, height, slope, and flow rate. Um, the first seven are when height was at 1, and the last five were when height was at 5 inches. Below are four graphs, two for when height was at 1 and two when height was at 5 inches. The top graphs show voltage versus current for the two data sets, and the bottom is the actual versus the projected power. Projected power being 100% because that would have been the maximum power of the flume, and the other series, series 1, is the actual output of power. You can see on the right side that there's a spike right when we added the 2 kilo ohm resistors, which shows that an increase of resistance on the circuit would have increased the generation of power.
The results of our experiment were successful in the way that they proved power generation with a small-scale turbine was very possible. Unfortunately, the data was limited by the constraints of the flume, and our team was unable to change the flow rate of the stream. Another roadblock that occurred was our team not having any power resistance in the motor, causing it not to generate any power. This was solved by adding a 2 kilo ohm resistor, which proved successful in allowing power generation to occur. In conclusion, with a little more resistance to the motor and a much more active stream, small-scale power generation with a small turbine will prove successful.